Welcome back, everybody. In this video, we'll be starting up Chapter 9. Chapter 9 is about inferences for two samples. So first thing, as always, what we want to do is look ahead and see what the chapter is about and then actually get into it. So just as a reminder, there are basically two main tasks in inferential statistics: estimating parameters using confidence intervals, and then testing claims about parameters, basically hypothesis testing. This chapter focuses on doing these things using two samples. So there are four sections in this chapter. So the first one, which we're going to work on here in this video, is 9.1, and it's about two proportions. So if we have two separate samples, or let's come up with a hypothetical. Let's say we have a set of buses in two cities. We'd like to know what is the proportion of buses that run on time in, let's say, Desert Hot Springs versus the proportion of buses that run on time in Palm Desert, let's say. Okay, section 9.2 is about comparing means for two independent samples. So we could compare the lifetime of light bulbs produced by a factory in Minnesota versus the lifetimes of light bulbs produced at a factory in Florida. And we want to compare the mean lifetimes of those two sets of light bulbs. Okay, a difference between 9.2 and 9.3 is that we're comparing matched pairs or dependent samples in 9.3. So in 9.2, the two samples will be independent, like light bulbs from one factory and light bulbs from another factory, or wherever you work, employees on the day shift versus employees on the night shift, let's say. 9.3 is about matched pairs. So maybe we want to compare the cholesterol levels in married couples. So the two people in the couple take a cholesterol test, and then those people are necessarily matched because they're a married couple, and presumably we can say that they probably eat about the same things and so on. So point is, though, that they are matched. They're not independent, because if we know one person out of the couple, we know the other person in the couple. Another example of a matched pairs kind of situation would be if we wanted to compare performance on a skill, and then give the subjects a training, and then have the subjects again measure their performance on the same skill, and we would ideally expect their time to completion on that skill to go down, right, if they've taken some training. But basically the before and after scores would be those matched values. Okay, but in any case, they're matched because it's the same individuals before and after scores. Okay, 9.4 is about comparing variances or standard deviations. Again, going back to like the light bulb example, we have a factory in Minnesota and a factory in Florida. They produce light bulbs. The lifetimes of those light bulbs can vary. Maybe the lifetimes of the factory in Minnesota, maybe those light bulbs vary less than the light bulbs produced in Florida, or maybe more. But we'd be comparing the variability, standard deviation or variance in two separate samples. So that's basically what chapter 9 is about doing the same kinds of things we've done before, looking at proportions, means, standard deviations and stuff, but this time it's about comparing two samples. In this section, we're working on proportions. Okay, so let's get started. So some of the fine print here, we want to be able to do both a hypothesis test and construct a confidence interval. For the confidence interval will be for the difference in the proportions. The hypothesis test will be a test of a claim about a proportion. So some definitions to begin with. We have two populations. We'll call them population 1 and population 2. P1 will be the population proportion. N1, the size of the first sample. So N is a sample size. X1 is the number of successes in the first sample, like the number of buses that run on time, let's say. N1 is the number of successes in the first sample. So P1 hat will be the sample proportion, X1 divided by N1. And then the complement of that, which is Q1 hat, will be 1 minus P1 hat. So we have a population proportion and then a sample size, a number of successes within that sample, and then we can construct a proportion out of it, and then look at the complement. We'll have the corresponding notations P2, N2, X2, P and Q hat 2 for the second population. Okay, so just to make sure that we understand what is going on here, let's try this example. It says from one distribution center, 32 deliveries were sampled and 30 were on time. At another center, 28 deliveries were sampled and 25 were on time. So we would like to know some of these numbers. So the two populations are going to be the two sets of deliveries from the two distribution centers. So let's see what we have. So N1, 32 deliveries, and X1 would be the number that were on time, that's 30. So P1 hat will be 30 out of 32. And then I'll give you a decimal in a minute for that. We have a second distribution center. They have 28 deliveries, out of which 25 were on time. And so we'll have a P2. Sorry, that should be a 2. That should be a 2. 25 out of 28. Okay. And then again, I'll give you a decimal for each of those. Okay, so we can look at the sample size for each of the two samples. That's the N1 and N2. The number of successes, in this case, it's on-time deliveries. Those are going to be the X1 and X2. And then the proportion, X1 out of N1 or X2 out of N2, are going to be our P1 and P2 hat. Okay, so let me give you some decimals for those two proportions. All right, so as decimals, for the first one, it works out to be 0.9375, and for the second one, about 0.8929. So the two on-time proportions of deliveries. Okay, one other piece of information we're going to need sometimes is what's called the pooled sample proportion. Here, what pooled means is where we just kind of put things together. So it's denoted by P with a bar on top, kind of like the X bar for the mean, but it's a P with a bar on top, and it combines two sample proportions into one proportion as shown here. So P bar will be X1 plus X2 divided by N1 plus N2. So going back to the delivery example we'd had a minute ago, for P bar, we'll have the total sample size on the bottom, which is 32 deliveries plus 28 deliveries. And then the on time, 30 out of the first one and 25 out of the second one. Okay, so let me go ahead and give you a decimal for that. So we have 55 divided by 60. And so that's about 0.917. Okay. So that's the pooled sample proportion, where we basically put all of the, in this case, deliveries together. All right, so the next thing that we're going to look at is some of the requirements that we're going to need to be true in order for us to do a hypothesis test. Okay, so for this, we need the sample proportions to come from simple random samples, and we generally assume that that's true. We need the samples to be independent for this. Okay, samples are independent if the sample value is selected from one population and not somehow related to or paired with values from the other population. Okay, we also need to have for the two samples at least 5 successes and at least 5 failures, so that NP hat should be bigger than 5 and NQ hat should be bigger than 5 for each of the two samples. Okay, so now the part involving the test statistic for the two proportions is a little complicated, so we're going to take a little time to take a look at it. All right, so this is the test statistic for two proportions. So take a few minutes to take a look at it, and that'll take us to the end of this video. And then in the next video, we'll go into some detail about how this formula works and then look at some applications of it. Okay, in the meantime, let me know if you have any questions, and then have a great day.